Welcome to the second screencast on electrochemical thermodynamics, in which we will discuss half reactions, the Nernst equation, and reference electrodes. In the previous module, we discussed how the equilibrium cell potential depends on the Gibbs free energy. Now, a cell consists of an anode and a cathode. And often in electrochemistry, we are not interested in studying the complete cell because then you're basically studying at least two reactions at the same time, which makes it more complex. So often we are interested in only either studying the anode or the cathode, and what that we call a half cell. Now, the half cell uh, potentials connect to the equilibrium cell potential via the following equation. So the equilibrium cell potential is equal to the potential of the cathode minus the potential of the anode. Now, a key question is, how do we come to the potentials of the half reactions? Because the Gibbs free energy is only connected to the complete reaction, so both the anode and the cathode. And if we now look at one of these half reactions, for example this one, we see there are electrons in this equation. Well, it's not that easy to find thermodynamic input values for electrons. So that makes it then difficult to assess the potential of such a reaction. So uh, electrochemists are quite pragmatic, so they found a solution, and basically the solution they have proposed is that they take one reaction, namely the hydrogen evolution from protons, this reaction, and they say, well, this reaction we say has a potential of 0 volts. And now we can use this kind of as the reference reaction. So if this reaction is 0 volt, then we can calculate the potential of all other reactions with respect to this reaction. And this you can practice in quiz question 2.3. Now, it is important to keep in mind that the potential you then calculate is not something physical. It doesn't have a physical meaning. It just basically is a convention. You say, I have a potential with respect to the standard hydrogen electrode. It's not a absolute potential. It doesn't mean that the reaction has a positive or negative potential. That has no physical meaning. Now, these standard electrode potentials, because that's how we call them, you can either calculate them from thermodynamic data, as you did in quiz question 2.3, but you can also just look them up on the internet. There are plenty of sources on electrochemical potentials you can find. Personally, I particularly like the electrochemical series in the handbook of chemistry and physics because it's quite extensive. This is a small excerpt from that. So basically the beginning starting with the A. And now if we look at, for example, the second reaction where silver plus electron gives silver, we can see that the potential of that reaction is 0.7996 volts with respect to the standard hydrogen reference electrode. So that applies to the reduction. At the same time, that potential also applies to the oxidation. So the electrode potential does not depend on the direction of the reaction because it's an equilibrium potential. So it doesn't matter what direction you go. The standard electrode potentials are given at 298 Kelvin, 25 degrees Celsius, 1 atmosphere, and 1 molar or 1 bar if we're talking for gases. Obviously, we don't have those concentrations and pressures in every electrochemical cell. So we might have systems with different concentrations and pressures. So how can we then calculate what the electrode potential is? For that, we can use the Nernst equation, which you have probably seen before in your career as a student. The equation basically shows how the electrode potential depends on the standard electrode potential and a term that depends on the activity of the oxidant and the reductant. Um, in practice, we hardly ever use the activity, but instead we use concentrations for liquid, and for gases we use the pressure in bar. We should, however, not forget that in reality there should be activities, and especially in electrochemical systems sometimes we work with highly concentrated systems, and then concentrations and activity can significantly differ. So this is something we need to take into account, is that when we use concentrations and pressures instead of activities, that we are making an assumption, and that we can introduce something that is not completely correct. Now, I would like to remark that this Nernst equation is only to determine the dependence on pressure and concentration, not on temperature. And the reason why I say that is because there is a temperature in here, but we should also keep in mind that the standard electrode potential is at 298 K. If you go to another temperature, that potential will change. So that's important to remember. Now, I can imagine that now things start to become a bit confusing, because in the previous screencast we discussed the equilibrium potential, how dependent on temperature, and now here we are discussing the electrode potentials and how they depend on pressure and concentration. To avoid any further confusion, I've made this overview table, which basically shows how both equilibrium cell potential and equilibrium electrode potentials can be determined at different conditions. So if we now look at this table, we see that at the standard condition, so 298 Kelvin, 1 atmosphere, 1 molar, we can say the equilibrium cell potential depends on the standard Gibbs energy divided by NF. And the equilibrium electrode potentials then relate to the cell potential via this equation. So the standard cathode potential minus the standard anode potential. Well, we can, as we just discussed, these standard electrode potentials can be looked up in tables that can be found on the internet, or you can also calculate them backwards, just as in quiz question 2.3. So those are the easy conditions. Now, if we now go to another temperature, then as we discussed in the previous screencast, we need to take into account the temperature dependence of the Gibbs free energy change. And if we fill that in, we get the equilibrium cell potential. And a simplification for that is that we use the entropy via this equation to determine the equilibrium potential at another temperature. Now, this is similar for the electrode potential. A similar equation applies as above, but now life is a bit more difficult in the sense that it's not possible to look up these electrode potentials um, from a table on the internet, because those are all at 298 Kelvin. So the only way to determine these value is by actually calculating them yourselves from the thermodynamic values. Now that's for then we're still stuck at 1 atmosphere and 1 molar. So now if we now go to the situation where we stay at 298 Kelvin, but instead go for different pressures and concentrations. So the equilibrium temperature of a potential as a function of pressure and concentration. Then we actually first look at the electrode potentials, where we say, hey, we can fill in the Nernst equation to determine this dependence for both a cathode and anode reaction. Um, where we can use the standard electrode potentials that we could just look up. So we fill in these equations, and by filling in these equations, you can then determine the equilibrium cell potential by deducing the electrode potential for the anode from the electrode potential for the cathode. So that's a, and now the last situation. So we want to determine something at a temperature, a different temperature, pressure, and concentration. So where do we start? Then again, we start on the right side with the electrode potentials. But now, obviously, we're not using the standard electrode potential to start with, but we use a temperature-dependent electrode potential to start with, basically the values that you see here, and that those we then correct for concentration and pressure, basically activity. And then you could do the same as what's basically given here, but that's not necessary. If you just want to know the equilibrium cell potential at this other temperature, pressure, and concentration, you actually don't have to calculate these values, because instead you can also say, well, I know my equilibrium cell potential, so I fill that in here, and I just take the second terms from the Nernst equation, and basically then you get the same equation as you had before, but you don't calculate these values. So I hope this overview helps to kind of see how do things depend temperature, pressure, and concentration, also to make the distinction more clearly between the equilibrium cell potential and the equilibrium electrode potential. Now, also to practice here, I recommend quiz questions 2.4 and 2.5. Now, now we jump to other reference electrodes, because until now we have discussed the standard hydrogen electrode potential. That's the electrochemical reference, but it's not an electrochemical reference we use in the laboratory, because that's it's too deep for this course to explain that, but that is just not a suitable reference electrode. So in practice, we use other reference electrodes to do our laboratory experiments, which we will explain more in depth in Module 7. But here we want to briefly discuss uh, what these reference electrodes are and how you can calculate their potential. By the way, what determines what makes a good a reference electrode is especially its stability. A reference electrode should always give the same potential and should not drift a lot over the course of an experiment, because then it's just it really affects your results, and that's what you don't want a reference electrode to do. Now, a key reference electrode is the so-called reversible hydrogen electrode. It is quite similar to the standard hydrogen electrode, but the standard hydrogen electrode is at where everything is 1 molar, so also the concentration of the protons is 1 molar in the standard hydrogen electrode. Instead, in the reversible hydrogen electrode, we take the proton concentration of the solution. So at pH 0, where the proton concentration is 1, then the value for the reversible hydrogen electrode is the same as the standard hydrogen electrode, but not in for the other pHs. So we can basically now just fill in the Nernst equation as we just learned. Uh, and well, the first part is 0 because the standard hydrogen electrode is 0. And then you see this dependence, and we can fill this in. So the oxidant in this case is the H plus. We have 2 H pluses, so that means we need this square here, and we divide it by the pressure of the H2. Now, normally our pressure is about 1 bar. So if we just say this is 1, then you're only stuck with the H plus, the square. So you can take out the 2, take that 2 out, and then you get the equation you end up with for the reversible hydrogen electrode is this one, minus 0.0592 multiplied by the pH. So that is the value of the reversible hydrogen electrode, which we often use in practice. Now, how does that in practice actually look like? You have a platinum plate, and you flush hydrogen past that platinum plate. And that's because platinum is a very good catalyst for hydrogen reactions. It really means that it is at equilibrium potential. So And then you can use this electrode as a reference material for any other electrode, which is probably on the other side of the salt bridge. Another commonly used reference electrode is the silver-silver chloride electrode. And the reaction, the equilibrium that occurs in that electrode is an equilibrium of silver chloride plus electron gives metallic silver and chloride. And here you see the system that it consists of, consisting of a silver chloride paste and a solution of KCl and Ag and silver chloride. Now, how do you calculate the potential of of such a reference electrode? Well, we take the standard electric potential for this reaction, which we can look up, 0.222. And then we still need to use the Nernst equation because this is a saturated solution. So actually you need to know the saturation concentration of the chloride in that solution, and that you then fill in. For the rest, you only have solids here, so you don't have to worry about that, but you do have to worry about the chloride concentration. If you actually do that, then you get to a potential of 0.197 volts versus the standard hydrogen electrode. Now, here, this is also the last slide of this screencast, and I recommend you to carry out quiz question 2.6 before we move to the next screencast. Thank you for your attention.